Look at linear first order differential equations and a couple of other types as well, but that's the main one I'm going to look at. So a quick note about separable differential equations. There's not really much derivation involved here. All you have to do is separate the variables onto each side, so get all of x on one side and all of y or the other variable on the other side, and then integrate both sides directly. So there's nothing too challenging about that. The linear first order differential equations, what I'll do is I'll derive the complete form that you can express y in terms of x, the final solution, and the general solution for y. So let's assume that you have a linear differential equation. So let's say you've got a function of x that you're expressing as a y prime plus a y with functions of x multiplying them. So this is a linear equation in y. So what you can do is rearrange this into this form. So I've just divided through by p of x to get it into a form where dy dx only has one multiplying it. So that's an easier form to work with. So now I'm going to start doing a bit of algebra and try and work out what y is by eventual integration. So I'm going to define f of x over p of x as g of x and q of x over p of x as h of x, like this, just to make the maths a little bit easier. Now the thing that you do is, this is hard to integrate directly because you can't, because the variables aren't separated, so you can't separate the y's and the x's, because we have a y here and an x here, a dy dx here, so you can't separate the y's and the x's. But what you can do is try and make this side look like the derivative of a product, which differentiates to give this, and then doing that you can then integrate both sides directly like a separable differential equation. So that's fairly easy to do. All you do is you multiply through by an integrating factor, which I've called I of x, which is just a simple function of x. So all I've done is multiply through by I of x, and what I'm saying is that I'm defining y of x multiplied by I of x as a product that I'm going to differentiate to give this. Okay, so give this thing that I multiplied I of x by. So I said the derivative of this is equal to dy dx multiplied by I of x plus di dx of y of x, which is just using the product rule here. I've just used the product rule on that, and I've said that that is equal to this thing here, just because I want it to be, basically, so I can try and express it as a derivative of my product. So then I can compare these two sides of the equation here, and I can say, well, this term is identical, so I don't need to worry about that. This term is slightly different, so we've got the y of x on both sides. So then that therefore implies that the di over dx is equal to hx I x. You can divide through by y of x if you can't instantly see it. So I've got this, which is separable because you can separate both sides. You can take the x's onto one side and then you can take the i's onto the other. So that's what I've done. I've taken the I onto this side, and the h of x stays here. You integrate directly and you get I of x is e to the power of integral of h of x dx. I didn't really explain where this comes from. Now, all I've done is that when I've integrated this, I said that it's just solving a separable differential equation. So the integral of 1 over I is natural log of I, and that's equal to this, which I don't know what h of x is, so I can't integrate it directly, but I can integrate this side. So given that, I know that I of x is equal to e to the power of this, because natural log of x is equal to this thing, so then I can just take e to the power of both sides like that. So then given this, I can now start to try and solve the linear first order differential equation. So I ended up with my product, which is what I was trying to do here. Come up with my product here, which is why I multiplied by the integrating factor in the first place. So I've said that is equal to this, and I've just substituted in the result that I've just got. And this bit here comes from the fact that the derivative of this is equal to this, and again I've substituted in the result that we've got for I of x. So here is this side here, because we said that this bit is equal to this. So I've just so these two are going to be equal to each other. So that's where that comes from. This was the original function on the left hand side, so that's where that comes from. So to simplify, so I've got integrating both sides, so yx, because all I've done is I've integrated this, so I get rid of the d over dx, so then I'm integrating this here. So then obviously you can see that to get y of x, all you have to do is divide by e to the power of the integral of hx dx. So this is what y is. And of course I can use my original equation, which is up here. So f of x is equal to px dy dx plus qx yx. So okay, so all I've done is I've substituted these in. So for any equation that you can write in the form of f of x is equal to px dy dx plus qx yx, then I can write it like this. So p of x is the thing that multiplies through by the dy over dx. Q of x is what multiplies through by y of x, and then f of x is the function on the other side. So that you can express any linear differential equation in this ultimate form. So that's where that all comes from. Just a little twiddle. This is not a linear differential equation, but it's one that can be made linear. It's called the Bernoulli equation. So it looks similar to the form that I have on this equation, this bit here, except that instead of having g of x, we've got a function of x multiplied by y to the power n. This is solved by making a simple substitution. You let v equal y to the power 1 minus n, and then you can differentiate this just using the normal rules to get dv over dy equals 1 minus n to y to the power minus n, and then therefore using the chain rule, dy dx is equal to dy dv dx, which is equal to the thing that the 1 over the thing that's we've just derived, multiplied by dv dx. So then if we substitute v into this equation, so if we substitute, so this thing is dy dx that we just put in, and then we've left the y's in for now because we can divide through by y to the n divided by 1 minus n. So that gets dv dx on its own, like this. This multiplier comes from the fact that we've divided through by 1 minus n, and then we get this thing here, y divided by y to the n, and then obviously on this side the y to the n goes as well. And you notice that this thing is equal to v, y 1 minus n. We've got y 1 minus n, so we can let that equal v, like that. And then obviously this is a linear differential equation. We've got dv dx on its own, okay. We've got a v here and then a function of x here. So this form is a bit like this form here. So all I've done is I've just used the same form here. It's not the same as this form because this form was a more general linear equation where we didn't divide through all the coefficients originally, which were functions of x, but it's this we're using this one here. So I've just substituted this form into here because it's a linear first order differential equation. Obviously we've got these constant terms here as well, but they're effectively just functions of x anyway because they're just constant terms, so they can come out the integrals. So I've just taken them out of each of the integrals, so that's not a problem. And then to get y of x, we just reverse the original substitution by doing v to the power of 1 over 1 minus n. So this is the final form of the equation.